Is a video tutorial in which I will go through the questions of the AP mock exam in year 2020 and explain the answers. We start with the first question. Which of the following represents the ground state of electron configuration for an atom of nitrogen? Nitrogen in the periodic table contains 7 electrons, and the electron configuration is 1s2, 2s2, 2p3, meaning that we have 2 electrons in the s, in the first s, another 2 electrons in the second sublevel s, and in the p orbital we have 3 electrons. Now if we follow Hund's rule, it explains to us that when the electrons are filled in the p sublevel, the electrons are filled singly, and then we start pairing the electrons. So if I have 3 electrons, the electrons are filled like this, and not like, for example, the one showing here. Here they started pairing the electron and they filled the p, which is not correct, which violates Hund's rule. So the final answer in this question, the correct answer is A. Moving on. Isotopes. Isotopes and relative abundance. When we look at the periodic table, the periodic table represents the average atomic mass of the elements, which is the calculated average of all the isotopes. So if we have isotope 1, let's say, we multiply it by the percentage of that isotope, we multiply it by its own percentage over 100, and then we keep on adding, like isotope 2 by its own percentage over 100, etc. until we calculate all the isotopes. This will give us the average atomic mass of the element represented in the periodic table. Now looking at this graph, it seems that we have 2 isotopes. So let's try to here calculate or almost find out the relative abundance of the first isotope, which is 187 atomic mass multiplied by, this is going to be around almost 62%. And for the other one, it is 185 multiplied by almost 30, and it's more than 35, between 20 and 40, 30, and then it's above 35, it's probably, I would take it 38. So plus 185 times 38% over 100. So if we did our calculations, we can find the mass to be 62. This is 115.94, and the other one is 70. So the final answer is 186.24. Now approximately, because I was taking abundances approximately, so I suppose that this is the correct answer. Now I can see that this one is far from being the answer, because our answer has to be somewhere around this. It has to be 186 point something. So 186.9, it's too close to the 187. So that's wrong. And it cannot be exactly 186 because the 2 isotopes, they don't have the same relative abundance. So this leaves us, and it can't be below 186, because the higher the 187 abundance is higher. So the answer is 186 something. So this is why also if we didn't do our calculations, the best choice is B. Moving on to the next question. No, wait, I skipped a question. A student found a beaker containing some powder and had a label of sodium chloride on it. Upon analyzing a sample of the powder, the following information was determined: the color, the mass of the powder, which means it includes the mass of Na and of Cl in it. Now the percent of sodium and the density. Which of the above information is the most helpful in determining if the powder is pure NaCl? Of course, not the density and not the color. And yes, in these kind of questions, we always take the percentage, because the mass will not give us if there is impurity or no, because this mass, it includes the mass of Na, the mass of Cl, and impurities. So the best information that we can take is the percentage of Na or the percentage of Cl if it was given in the table. So it's D. Moving on. Consider the photoelectron spectrum of element Q given below. Which peak R or T corresponds to the 1s electron? Always when you are looking at such graphs, determine on which side, look at the binding energy to determine on which side are the valence electron. Keep in mind that inner electrons needs higher energy to remove them compared to the outer valence electrons. So here 7, this is the highest binding energy on the graph, and here goes to 0. So this means here we start with valence and here we have inner. Now this is in the configuration, we always start 1s, 2s, 2p, 3s, etc. So here we have 2 peaks. So it's the 1s2 and the 2s. Now look at peak T. It's half of the peak of R. So the first one is 1s2 and the second peak is 2s1. So so what do they want? Which peak corresponds to the 1s? It is R. Yes, because inner electrons will have the strongest attraction to the nucleus. Moving on, which of the following is the best explanation of why the atomic radius of sodium is greater than the atomic radius of Cl? So we're talking about the size. Now, sodium and chlorine, I'll show you on the periodic table. They both belong to period 3. So let me just split here. We're looking at period 3. We're looking at period 3 elements, sodium, and at the end in group 17 we have chlorine. So they both belong to period 3. Now, according to the periodic trends, the atomic radii decreases across the period. So as I'm going from left to right, let me just show you. This is sodium. This is magnesium. It gets smaller. This is aluminium. It's not showing the... Okay, it gets smaller simply for the reason that as I'm going throughout the period, The number of inner electrons, the shielding effect, is constant because the electrons are the same in the energy level 1 and 2. Those are the inner electrons. So the shielding effect is constant, but across a period, the number of protons, the effective nuclear charge of the neutron of the nucleus is increasing. Like sodium contain 11 protons, magnesium contain 12 protons, aluminium 13, and so on until we reach chlorine 17 protons. So for the same shielding effect, the attractive pull coming from the nucleus is increasing as we go from sodium to chlorine. This is the reason why the atomic radius of sodium is bigger than the atomic radius of chlorine, because the attractive pull coming from the nucleus in Cl is greater. And this is it. It's the effective nuclear charge of Cl. Now, when gallium forms an ionic compound, it has a charge of, because it. Now, if you look at the periodic table, gallium belongs to group 13. So here's gallium. It belongs to group 13. So elements of a group 13, they lose 3 electrons, so they make a charge of 3 plus, simply because they lose 3 electrons. So the best choice here, because they have 3 valence electrons that they will lose. So the best choice is C. Moving on in the questions, consider the following Lewis diagram X and Y for carbon dioxide CO2. Diagram, okay, X or Y is the more likely structure of CO2. Now, this is an easy question. So here's diagram X. This is the correct one. Now, we always, when we do Lewis structure, we always consider the formal charge, which will help us determine the most stable structure. I'm gonna go through the steps of drawing and explain to you how we get the formal charge so that you can know why the answer is, why C is the correct answer. Okay. So, first of all, when we look at CO2, we count the valence electron in this molecule in order to draw it and distribute. So carbon has 4 valence electrons, oxygen has 6 valence electrons. Since we have we have 2 atoms of oxygen, so we times 6 by 2, and the total we have 16 electrons to distribute, or in other words 8 pairs to distribute. So when we put the carbon, we connect the central atom by terminal atoms. So 1, 2 pairs distributed. Then we distribute, we complete the octet rule of the terminal atoms. 3, 4, 5, 6, 7, 8. Now, when we're done with this part, we check the central atom. If the central atom completed the octet rule, then we're done. But in this case here, the central atom did not complete the octet rule. So we start removing from the terminal and putting it as a shared pair between the central and the terminal. We have 2 ways to do that. We can remove 2 pairs from one of the terminal atoms and placing it as a common pair between C and O, or we can do like this. So 1 from this side and from the other terminal. And that's why we have 2 diagrams, X and Y. Now the formal charge will help us here determine which one is the best. So how to do that? We need to calculate the formal charge. and the lowest possible equal to zero formal charge will be for the most stable molecule. So calculating the formal charge in this molecule, let's take diagram Y. Starting by the formal charge of carbon. So formal charge is equal to the valence electrons of carbon minus half the bonding electrons in carbon minus the non-bonding electrons. So carbon has 4 bonding electrons minus half non-bonding. We have 0 non-bonding because all the electrons of carbon are bonded. Minus the bonding, minus half the bonding. So 1, 2, 3, 4, 5, 6, 7, 8 minus 0 the non-bonding. So it is equal to 0. So the formal charge of C is 0, which is good. Now, the formal charge of this O, so I'm going to name it O star, it's equal to 6 valence electrons in O minus half the bonding, which is 6 here, half the bonding, minus 2 non-bonding. So that makes it 6 minus 3 minus 2 equal to 1. So this oxygen has a 1 formal charge. And the other oxygen, this one over here, it has 6 valence minus half bonding, 2 bonding electrons, minus 6 non-bonding. And that is equal to 6 minus 1, 5 minus 6, negative 1. This is a formula with C, 0 formal charge, but O and O, they both have a non-equal to 0 formal charge. So this one is not really stable. Going to the other one, C, we have valence electron of C minus half bonding. So 1, 2, 3, 4, 5, 6, 7, 8 minus non-bonding. All the electrons of carbon are bonding. So 4 minus 4, that's a 0. This O and this O will have the same formal charge. So 6 minus half bonding electrons in O, 1, 2, 3, 4. Every O has 4 bonding electrons and 4 non-bonding. So that is equal to 0. So this is the most stable formula or Lewis structure of CO2 because all the atoms have 0 formal charge. No, wait, it is X, sorry. This is X because all of them, they have a 0 formal charge. Next, the crystal structure of sodium chloride NaCl is shown in the diagram below. Okay, this is a crystal lattice structure, a Cl minus, always the positive ion is the smaller one, held by electrostatic forces. So in terms of electrical conductivity, of course, an ionic salt cannot conduct electricity in the solid state, but it conducts electricity when molten or dissolved, because at that point the ions are free. Now, right now, being in this crystal lattice, ions are not free. They cannot move. They are held by the strong electrostatic forces between Na plus and Cl minus. Now let's read the question. In terms of electrical conductivity, which of the following statements correctly compares molten to crystalline? Okay, NaCl composed of Na plus and Cl minus ions. This is the molten. that can move. Yes, they can move in the molten state and conduct electricity. While in the crystalline structure, the electrons are locked. They're not free. Does not have free moving electrons that can move and conduct electricity. This is the best choice. It has nothing to do with the transfer of electrons. NaCl crystalline ions are held in fixed positions, but in the molten, no. And here it's saying that the molten does not have free electrons, which is not correct. So the best choice is A. Sorry. We continue. According to the Lewis diagram of water given HOH, the bond angle is closest to. Now, this one is a tetrahedral electron geometry and specifically bent shape, with O having two lone pairs and two bonding domains. So two non-bonding and two bonding. So if we look at a tetrahedral shape, which is like this is a tetrahedral electron geometry. Usually in a tetrahedral electron geometry, the electrons are held by, the angle is 109.5 between all the domains. However, with the first bonding, with the first lone, if there is one lone pair, the bond between the bond angle becomes less than 109.5, which is approximately 107. Now H2O has two lone pairs, and the angle, it goes a bit below 107, which is almost equal to 104.5. So that's the correct bond angle. A gaseous fuel mixture is in a sealed container with a piston. Okay, we're talking about gases mixture. We have them in a sealed container with an initial volume of 600 milliliter at a pressure of 1 atmosphere. If the piston has been moved to reduce the volume to 40 milliliter at constant temperature, here we go. This is Boyle's law. Assuming ideal gas behavior, then the new pressure of the mixture is close to what? From 600 to 40, the one is going to increase, because in Boyle's law, volume and the pressure are inversely proportional to each other. Now in your formula sheet, you have, I don't have the formula sheet here, but in the formula sheet given to you, it shows the formula of Boyle's law. I can show it to you here. I have a booklet of the formulas here. So you have the of ideal gas law, the formula of ideal gas law. If we remove, if this is equal to a constant, so every time pressure times volume equals the new pressure times volume equals the new pressure times volume. So they are inversely proportional. So PV equal P1 V1 equal P2 V2. So we continue. Here 600 times 1 equal 40 times the new pressure, and that is equal to 15. They're inversely proportional. Sorry. Now, equimolar samples. Equimolar means I have the same number of moles in the samples that we have. So N of CH4 equals the molar of the moles of propane. They are in identical sealed container. Okay. So N is the same. I have two containers at the same conditions of temperature and pressure. Okay. Now, since mole and temperature and pressure are the same, so definitely they will have the same volume. They will have the same volume. Now, the question is, the C3H8 deviates from the ideal behavior, more than CH4, which is true. Which of the following statements best explains this deviation? Now, when we are talking about ideal gas behavior, the gases with the weakest intermolecular forces, especially the gases with the weakest intermolecular forces are usually closer to be considered closer to the ideal gas behavior. Now, in a question like this, we need to compare the intermolecular forces of CH4 to the intermolecular forces of C3H8. Now, both molecules are nonpolar. So both molecules, they have London dispersion forces. They don't have any intermolecular forces of dipole-dipole interactions nor hydrogen bonding. So here we are dealing with the same kind of intermolecular forces. However, why C3H8 deviates more? Why the intermolecular forces in C3H8 are higher than those of CH4? In this case, we compare the electron cloud and the molar mass of the two molecules. As you can see, this one has one carbon, this one has 3 carbons. So the molar mass in here is higher than the molar mass of the other one. And in this case, the electron cloud of C3H8 is larger, and the C3H8 has more polarization. So therefore, the intermolecular forces of C3H8 are stronger than the intermolecular forces of CH4, and that's the reason why it deviates. Moving on. What is the volume of 0.2 molar HNO3 stock solution? What is the volume of 0.2 molar HNO3 stock solution is to be used to prepare 500 milliliter of 0.05 molar HNO3. So we're talking here about taking a stock solution and taking a sample of it to dilute in order to prepare a lower concentration. So C1V1 equals C2V2. So that's a 0.2 molarity times the volume. What's the volume to use in order to prepare a 0.0500 new diluted solution and a 500 molar? So if we do our calculations, the answer is 125 milliliter. Moving on, the mass of sodium chloride and ACl needed. What's the mass of sodium chloride and ACl needed to prepare 200 milli of a 0.5 molar and ACl solution? In your formula sheet, we need to consider these formulas, the mass over the molar mass, and here we are doing some preparations. We want to prepare 200 milliliter of a certain molarity, and the molarity is the number of moles per volume. So first of all, we need to find the moles of this concentration, this solution, and then placing the mole here, then we can identify how much mass is needed. So in this case, we multiply the molarity. I'm starting in this formula. We multiply the molarity by the volume. Of course, do not forget to convert the volume into liter. And placing N here, we need to multiply it by the molar mass in order to get the mass needed. So I'm going to write here the mass needed, and I'm going to multiply it by the molar mass. If I include the formulas, it's 0.50 mole per volume, mole per liter, multiplied by 200 liter, so that cancels out the liter, multiplied by 58 gram per mole, that cancels out the mole. Doing the calculations, the answer would be 5.8, so approximately 6 grams. Question number 14. A 71 gram sample of sodium sulfate and Na2SO4 was used to prepare 500 milliliter solution. What is the molarity? So basically the same procedure, but calculating now the molarity. First, we need to, in order to calculate the molarity, we need to divide the given mass by the molar mass. And we need to divide it by the volume in order to calculate the molarity. So that is equal to 1 molar. Moving on. Question 15. Which of the following statements best explains what happens as photons of visible light are absorbed by colored dye molecule? Okay. Every solution has a color, and there is a certain wavelength at which there will be maximum absorbance. So let's read the choices and eliminate the wrong answers. So the photons of visible light, so this is the light that we see, are absorbed by colored dye molecule. Specific covalent bonds in the dye molecules start to break and reform with the bond energies of the bonds being the same energy. This is completely nonsense. It has nothing to do with the breaking the bonds. The dye molecules start to rotate faster in specific modes with a difference in energy between lower and higher rotational states. No, when we direct a light, the rotation stays the same. It doesn't change. This is not the correct answer. Specific chemical bonds in the dye molecule starts to stretch and bend. So basically this is very similar to choice B, with a difference in energy between the lower and higher vibrational states. No, it has to do with the electrons. We're talking about photon and absorbance that is done by the electrons. They can become excited and move to a higher or lower state. When an atom is hit with light, the electrons of that atom becomes excited and they can move to a higher energy level. However, the electron doesn't stay in the higher energy level. It will again release this energy in form of light, colors, meaning color, because the light has different wavelengths. So every light energy will have a different wavelength, and we see it as a color. And the electron, as it emits this light, it goes back to its lower original state. So here it's choice D. Certain electrons in the dye molecule move to a higher energy level upon hitting it with a light, with the difference in energy between the lower and higher energy levels being the same as the energy of the absorbed photon. So this is the correct answer. Moving on. Okay. Using a spectrophotometer, a student measures the absorbance of a solution containing iron thiocyanate ion. The cuvette the student used has two opaque walls and two transparent walls. Your fingers always have to be placed on the opaque walls, so that because the opaque wall, we do not put them in front of the light. The light will go through the transparent walls, and we must not hold the cuvette on the transparent walls, because we will affect the absorbance. Our fingerprints will affect the absorbance. So, which makes the absorbance higher. Now, the student arranged the cuvette correctly so that the path of light passes through the transparent sides of the cuvette while calibrating the spectrophotometer. If the student arranges the cuvette incorrectly, so meaning if the light, so let's say this is the light and this is the cuvette. Okay. So if the light goes through this shaded opaque walls, the light will be we will get wrong data, because like too much absorbance. It has to be clear so that the light can pass. Now, if the shaded walls were here, and the light is going from this direction, I hope that my drawing is a bit clear. So going through the unshaded area, it will show you the maximum absorbance. However, if you have fingerprints on this area and you held it with your fingers, the absorbance will be affected, reflecting a higher absorbance. So let's continue the question. If the student arranges the cuvette incorrectly so that the path of light passes through the opaque sides of the cuvette, so either fingerprints or opaque sides, the absorbance will be higher. How the absorbance will be affected? Definitely it will be higher. Higher. So the correct answer is C. Now, in the reaction below, C6H5N acts as. Okay, here we're dealing with acid and base. Definitely not conjugate, because conjugate is what we obtain after acid and base transfer their proton. So it's either a base, a bronsted-lowry base, or a bronsted-lowry acid. Now looking at it, this proton was donated to this one. See over here. So that's a bronsted-lowry acid, being an H proton, H plus donor, and being an acceptor, it's a base, bronsted-lowry base. Consider the following reaction and its rate law. Okay. This is a second order reaction, being first order in CH3I and first order in KOH. In your formula sheet, you have the formula of a second order reaction and first as well. So let's see the question. What do they want first? Which of the following statement is correct? If the concentration of CH3I and KOH are halved, the rate must be halved for each. So if both of them were halved, the rate will be decreased by 4. A larger amount of CH3OH, no. The rate will not affect the amount. The rate will show you how whether we're going to obtain CH3OH faster or slower. So not A. If the concentration of CH3I is doubled, so first the rate is gonna double, keeping the concentration of KOH constant. So if first order doubled, then the rate will double. So this is correct. Now let me just go through the other options. If the concentration of both doubled, so if this was doubled and this was doubled, the rate will quadruple, because 2 times 2 is equal to 4. So not double, it will quadruple. You know, this is how we do it. 2 to the power of 1, because we doubled to the same order, equal 4. This is how we know that the rate will quadruple. If the temperature of the reaction is increased, the rate will decrease. That's not correct. They're directly proportional. The rate is affected by temperature as well, but it increases as the temperature increases. Magnesium solid reacts with HNO3 according to the below equation. A student carried out 2 kinetic experiments to investigate the rate of the reaction. So in experiment 1, the student added 4 gram pieces of magnesium. And here powder. So here he added a big chunk of magnesium, and here we added the same mass but powdered. So the surface area in contact with the acid solution is larger. So in this one, the reaction is going to be faster, because we have more collision, more particles exposed with the solution with the acid of nitric acid, so which increases the frequency of collisions, and the reaction will be faster. So here, okay, so they determined the rate of the reaction by measuring the volume of the collected hydrogen gas. Now, the initial rate of the experiment, okay, which one is faster? Experiment 2 is faster because it's not about the concentration. We used same concentration, so it's about the larger surface area. Next question. Consider the following reaction: N2O4 dinitrogen pentoxide decomposing into nitrogen dioxide and oxygen. If the concentration of N2O5 was measured over time, the following graphs were obtained. So when we look at the rate of consumption of N2O5 throughout the time, or the progress of the reaction always starts fast and slows down. The rate is not linear, and it doesn't increase over, wait, this is 1 over. So let's look at the question. This one, if the concentration was measured over time, the following graphs, okay. Here we're looking at the order of this reaction. Okay, so this is correct. Oh, this is Lin. Actually, I didn't see Lin here. So this is Lin. Well, these are the graphs of the first order reaction. First order reaction. Because a zero order reaction is independent of the concentration of N2O5. And a second order reaction is not like this graph. So we can say that this is a first order reaction from the graphs. Okay. Moving on. Uranium 238 follows a first order radioactive decay to thorium. Okay. By the release of alpha particle, the nuclear equation that represents the process is given. Which of the following, when plotted against time, will produce a straight line? Well, let me takes you back to this one. Ln will give you a straight line. So ln of the concentration of uranium being first order, because the nuclear isotopes, they have a first order decay. So the first half-life, the second half-life, it's always a linear shape. The gas phase decomposition of nitrous oxide has the following two-step mechanism. Okay, we always look at this law because this is the rate determining step. Okay, the chemical, and from the rate determining step, we can write the rate law. Now the chemical equation of the overall reaction is, and the rate law is. So first, let's add these two equations together. This cancels out. N2 and N2 from the same side will be added. So we have 2N2, 1O2, and N2O plus, 2 N2O. So as an equation, overall equation in A and D are both correct. Now, looking at the rate of always, we can write the formula of the rate law using the slow step, not the fast. So it is equal to the slow step. It's only the reactant. We in the rate formula of the rate law, it's always equal R equal to the constant multiplied by the concentration of reactant. Okay, so in the fast step here, they're writing the rate law from the fastest step, which is not correct. We always rely on the slowest step to write the rate law, and it's equal to the concentration of N2O. That is the correct answer. Now again, okay, I guess this is the same question, right? No. Okay, consider the following reaction. Okay, we need to find the rate law. This is an equilibrium. Okay, and this is the rate determining step. So from step 1, we can write K equilibrium to be N2O2 over NO squared, because this is an equilibrium. Now from step 2, we can write the formula of the rate law. We always rely on the slow step to write the formula of the rate law. So it is K multiplied by N2O2 multiplied by O2. Now, we need to use the formula written above in order to change the N2O2. So, if we take this N2O2, okay, let me just move this a bit here. So from step 2, we can write the rate law as K multiplied by N2O2 times O2. Now, using the formula of K equilibrium, we can take N2O2 to be equal to K equilibrium multiplied by NO squared. Then we can substitute this value into the formula here. So the rate law is K times K equilibrium, which is also a constant, so we can write it as K, just K, multiplied by NO squared times O2. So this is a third order reaction, and the final answer is D. Moving on, the diagram below shows the distribution of molecular energies for equimolar samples of a certain reactant at 4 different temperatures. According to the diagram below, so this is the activation energy, and these are some molecules colliding with each other in order to react. The reactant will be consumed at the fastest rate, of course, at a higher temperature. Now let's see. Okay, let's understand the graph. This is Max Boltzmann graph. I think this is how we call it. So what's happening here is that as the molecular energy is increasing, meaning here majority of the sample has less energy, majority of the sample has a bit higher energy, majority of the sample has, why I'm saying majority, because this is the maximum fraction. Okay, so this, like most of the molecules, they are having this kind of energy at this temperature. Now, for temperature 2, more molecular energy. You look at the x-axis over here. So obviously, T1 is less than T2. Now, obviously, T2 less than T3. And here, the maximum, this value is higher, less than T4. Of course, as we increase the temperature, the reaction goes faster and the molecules colliding will be closer from their activation energy. So in this question, they want to know the reactant will be consumed at the fastest rate, of course, at temperature 4, because, okay, let's see here. This is the only choice with T4 because the molecules, yes, of course, they have a higher kinetic energy. Yes, and it's close to the activation energy. Now another question, the pH of 1 times 10 to the power negative 3 nitric acid. This is a strong acid that will ionize completely for giving us an H plus and NO3 minus. So whatever concentration that we have, it's going to be fully turned into the H plus concentration. So doing minus log, pH is minus log H3O plus or H plus. The answer is 3. Approximately 3 because this is a strong acid. So that's the correct choice. Next question. The diagram below represents the reaction energy profiles for a reaction in the absence of a catalyst. Of course. And so here without a catalyst, because the activation energy is higher, catalyst. And the role of a catalyst is to lower the activation energy and speeds up the reaction. So with catalyst, the reaction energy profile for the catalyzed reaction, okay, is S, of course, because, so let's read, an increase in the number of transition states. No, it has nothing to do with the steps of the reaction, the internal steps of the reactions, the step mechanism of the reaction. So it is D, because the catalyst lower the activation energy by offering an alternative pathway. So it's option D. Consider the following equation that represents the reaction between C2H2 and O2. C2H2, okay, plus O2 is an exothermic reaction since it is releasing 2600 kilojoule. Anyway, this is always the combustion when a substance reacts with oxygen to produce CO2 and H2O. This is a combustion reaction. So let's see the question. Now, if you pay attention here, this amount of energy released per 2 moles of C2H2. So 2 moles of C2H2 release 2600 kilojoules of energy. Now, what would be the amount released by 1 mole? So definitely it's half the quantity. That's the answer. Next, the graph below represents the changes in the temperature recorded for 2 liters of H2O surrounding a constant volume container with a 1 gram sample of benzoic acid has been combusted. Oh, calorimeter. So we are doing the combustion of benzoic acid. Benzoic acid reacted with oxygen, of course, in order to produce CO2 and H2O and some amount of energy. So we have 2 liters of H2O in which we are going to see, for which we are going to see how much the temperature is going to change. In order to know, with this variation of temperature, we can know how much energy was released by this combustion, by this 1 gram sample of benzoic acid. So the specific heat capacity of water is 4.2 and heat was not lost. So the container, the calorimeter is perfectly sealed. And the density of water is 1 gram per milliliter. So we use the density in order to find the mass of water, because in the formula of heat, it is MC delta T. So we use the mass of water and not the volume of water. So having a density of 1 gram per milliliter, multiplying the 1 gram per milliliter by 2 liter, which is 2000 milliliter, we find the mass to be 2000 grams. Okay, now okay, let's look at the graph in order to find the heat released from the combustion. So whatever heat released from benzoic acid, it's the same absorbed by the water. So by calculating the Q of water, we can know how much heat was released. So it is 2000 grams of MCM times C. So this is grams. The specific heat capacity of water, gram Celsius, and we're gonna do T final minus T initial. So 25 is our T final, And our T initial probably is 22 point, let's say 1, 2, 3, wait, let me just, 2, 3, 4, 5. So it's 22.1. Okay, doing our calculation, times 4.2 times 2000, it's going to be equal to 24,360 joules, which is equal to 24.36 kilojoule. And that's the correct answer. Now, almost reaching the last question. Before the last, consider the following balanced equations, CO and H2O, to give CO2 and H2. Based on the standard enthalpies of formation given in the table below, the approximate enthalpy changed of the reaction is. When we look at the enthalpy of formation, the enthalpy of formation is equal to the sum of the enthalpy of formation of products minus the sum of the enthalpy of formation of reactant. Meaning, the enthalpy of formation of hydrogen plus the enthalpy of formation of CO2 minus, so I can remove this, minus the enthalpy of formation of H2O plus the enthalpy of formation of CO. So it's always products minus reactants. Now, in this table, we don't find H2 simply because the enthalpy of formation of H2 is 0 minus the one of CO2 is negative 394 minus the one of H2O is negative 242 and the one of CO is negative 111. So plugging this into our calculator, we obtain negative 41 kilojoule. The final answer in our video, the final question on our video recording: a student dissolved 4 grams of ammonium chloride in 1 grams of water in a coffee cup calorimeter. The diagram below shows the laboratory setup for the experiment with the initial and final temperatures of the mixtures in degrees Celsius. So this is the initial. It's 20.05. Oh wait, this is 20.246830. 22, sorry, I want to say 20, 22, 24. Let me clarify it. So 22, 24, 26, 28, 30 degrees Celsius. So this being between the 20 and the 22, so the initial temperature is 21 degrees Celsius. The final temperature is 22 degrees Celsius. So the student 4 grams in 1 grams of water. Okay, so they want wait. Sorry for this mistake. Let me look properly. So this is 20. The 20 is here. Okay. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So it is 25.5 degrees Celsius. And the final is 20. So they want the delta T, final temperature, final minus initial. So it is 20 minus 25.5. The final answer is 5.5. Okay. Now, we need to look at the significant figures. Now, it is this one. Because with the scale of this graduated cylinder, we cannot, it's 25.5 and it's 20.0. Okay, so the final answer is C. And that's it. Thank you for listening.